All right. Okay. So it's week one Wednesday, and we are moving right along. Uh, on Monday, we covered chapters 1 and chapters 2, and now we're going to look at chapter 3. Before we get into that, just to kind of, I guess, a few reminders of just how like deadlines are going to work. So pretty much every week, you're going to have kind of, it's like the same pattern every week. Okay. So every week on Wednesday, in discussion, your TA Eric will introduce a new lab, and that lab will be due the following Tuesday. Okay, so you basically get like 6 days to work on it. Okay, so lab 1 is going to be due this coming Tuesday, August 10th, 6 p.m. Make sure you knit it, to a PDF, and you're going to upload that to Gradescope. The first lab is the hardest one. Not because the lab itself is hard, the questions themselves are easy, but it's just there's a whole lot of stuff going on with kind of setting things up, right? Maybe some of you have worked with R before, and so this is fine, but probably 98% of you, 99% of you have not really worked with R before. So you got to download R, you got to download R Studio, you got to install those things, you got to install like packages like the R Markdown and the tidyverse and this and that and this and that. And there's just a whole bunch of stuff going on, right? And unless you do all of these things correctly, it's not going to work, right? You're going to get errors and things, and it can be frustrating, right? So please do not hesitate to ask questions on CampusWire. I can answer, Eric can answer, your classmates can answer, okay? Come to office hours. I'm happy to help. On Zoom, you can share your screen, and I can be like, oh, you know what, this is what's going on, right? Sometimes you're having issues, and you don't even know what you're supposed to be looking for, but I've been doing this for a while, so I can easily look at your screen and be like, oh yeah, this is the problem with what's going on. So I'm here, and Eric's here, and even your classmates can help you there, right? So here's everyone, I hope, has joined CampusWire. Okay, there's not a whole lot of activity going on there right now, but post your questions. You don't have to be embarrassed about any questions, right? So most likely other students are struggling and stuff like that. And your questions will benefit others, right? These are my office hours. I've got pretty much I've got like 5 50-minute, 1 hour, 50-minute sessions, Mondays at 6, Wednesdays at 6, and then Tuesdays and Thursdays at 10, and also Saturday mornings at 10. The weekday office hours uses the same link as this lecture. So, you guys are here, you can use that. The Saturday one uses a different link. Just keep that in mind. So be sure to go on CCLE to look up the link. It's a different one for Saturday, okay? Your first homework assignment is due on Sunday, all right? So this coming Sunday, you have to upload it to Gradescope, and some people had questions, but yeah, I imagine most of you are just going to write your answers on a piece of paper, and then you're going to use your phone to scan it, and then you're going to upload that scan, right? Some of you actually have a physical scanner where you can like feed your papers in and stuff, and you can use that. And then some of you have a tablet like an iPad, and you've got like the Apple Pencil, and you can do your homework on the tablet and things like that. And you can, just save it as a PDF and upload it, right? It doesn't matter. Just make sure. So this is really the only important thing. Make sure you clearly number your problems, because all the grader is going to do, they're just going to kind of look and just count the number of problems you've done. And if you've done all the problems, you're going to get 100% on the homework, okay? It's just done on completion. They're not going to check to see if your answers are correct. I think I've posted answers to most of the homework problems, maybe not all of them, but it's up to you to kind of verify your own work. Make sure you've got a handle on the questions and things like that. Okay. Any questions about how to do your homework? Okay. And that's going to be due Sunday. All right. And then and you're going to have your first quiz this weekend. Okay. And it's going to get released. So the quiz will be released on Saturday at noon, and you have to take the quiz within this 36-hour window from Saturday at noon to Sunday, basically midnight, 11:59 p.m. Okay, and you'll have 1 hour to take the quiz, and you take it straight just in your browser. You'll click the link. It takes you to Gradescope. The questions will be there, and you answer it. Okay. Quizzes are open note, open book. You can use a calculator. You can use R if you want, as to kind of help you with your calculators and stuff. Obviously, it's a quiz, so don't discuss the quiz questions with other students. Don't discuss your answers with other students. Most of the questions are going to be short answer. Some of them are going to be multiple choice. Basically, it'll say like, it'll ask you a question like, what's the probability of this, right? And you just type in a number, 0.23, okay? And then that's it, okay? Usually, some of the questions will be kind of grouped together. So I might give you like a small data set or small set of numbers, and I'll say like, find the median and find Q1 and find Q3. And, you know, if you make a box plot, where's the upper fence and how many outliers do you have or something like that, okay? And so you just type in your numbers. Gradescope's going to auto grade these things, okay? And if your answer is right, you get the points. And if not, it doesn't give it. It basically says it's wrong, okay? There will be a spot at the end of the quiz where you can, where you have the option to upload a file, basically your Scratch work for some partial credit, okay? And this is optional. You don't have to do it, but basically, if you get a question wrong, you know, you're gonna get 0 points. But if we look at your Scratch work and it's like, oh, you did all the steps correct, but you made a small mistake here, we can give you some partial credit. Obviously, we can't give you 100% for it, but we can give you some of the points back, okay? And so that's optional. And you're gonna scan it and upload it just like you do the homework, right? So you'll scan it on your phone and then you'll put it in, there's a spot in Gradescope to upload, okay? Question says, how many questions are on the quiz? The answer is, it depends from quiz to quiz. And, as we go through the materials, certainly some material is easier than others. And so it's going to depend. I think the quizzes, I'm fairly generous with the time. No one in the past has complained that they didn't have enough time to complete the quiz, right? So you get an hour to complete the quiz. And I'm pretty sure I feel like that's going to be plenty of time. I'll say for most of you, okay? Like the vast majority of you in it. And, sometimes I say like, people don't complain. And then I don't want anybody to feel like, oh man, I struggled with time and, am I not as smart as my classmates or something? That's just not the case, right? We all each have different strengths and weaknesses. And, some of us, when it comes to test taking, like we're a little bit slower than others, and it's not a big deal. But yeah, you have an hour. It's designed, kind of 45 minutes to answer questions and 15 minutes for uploading and scanning your Scratch work. But if you want to spend all 60 minutes to kind of just answer the questions and not bother with the uploading, that's also fine. So the exact number of questions, I don't know off the top of my head. I feel like it's a fair amount of time to complete the quiz. Okay, any questions on this? Okay, and this is pretty much going to be the cycle every week. Okay, every week you're going to have a quiz, a homework, and a lab due. Okay, and it's going to be like this. And so you're going to have 5 quizzes, 5 labs, 5 homeworks, and that'll take us to week 6. And then during week 6, and then that's our last week, and you'll have your final exam. There's a little bit of like an oddity in that quiz 5 is going to be due like Sunday of week 6, and then it's like Labor Day, and then you take the final. So it's kind of like you have a quiz and then you have a final exam, but that's just that just happens because there's Labor Day scheduled in there. So in the syllabus, and I think Eric covered this, right? So normally we would have 2 sessions per week, and we have 6 weeks, and we would have 12 sessions. But Monday of week 6 is Labor Day. And so that cuts us down to 11 sessions. And what that does is I like to hold a review session for the final exam, okay? And so my solution is I'm gonna have kind of an optional session on Friday of week 5, okay? So that's in the calendar, I think. So, we'll same link right here, Friday, week 5. And I'll give you guys a reminder, but there'll be a review session for the final exam on Friday of week 5. And hopefully that will help you prepare well for the final exam. So I just kind of just want to make sure you're aware of that. Okay. All right. I guess, yeah, one more time. Any questions before I get started in today's lecture content, lecture material? Any comments? Do we feel okay about the lab, the homework, kind of stuff? All right. Okay. All right. Well then, okay. Thank you. Thank you for that thumbs up. What did I say? Oh, okay. Yes. Chapter 3, probability. That's what we're doing today. I'll take a sip here. Okay. All right. Oh, learning objectives. So we are going to, this is just kind of like, this is hopefully what we'll cover. Not hopefully, this is what we'll cover. So we'll talk about the definition of probability, and we've got a theoretic and an empirical definition of probability. We'll cover rules for finding probabilities, and we've got conditional probabilities. And when you talk about conditional probabilities, there's also this concept of independent events, whether events are independent, and we'll even talk about what that even means in the first place. And then we will introduce random variables, and that's a very important concept, just because pretty much after this lecture, we're going to be dealing with random variables a lot, okay? And part of dealing with random variables is going to be finding the mean and standard deviation of a random variable. So let's just back up for a moment, right? So a lot of times when you take a stats course, the title of the course might be statistics and probability and statistics or something like that. And I can't imagine an introductory statistics course that doesn't mention probability, right? Like it's a key central idea and central kind of piece here. And, are they the same thing? Are they different? They're different. The ideas of probability is different from the subject of statistics, but they are very much related, okay? In kind of the way that grammar is different from maybe like composition and writing, but it's very important, right? Grammar is a separate aspect, but it's very much related to kind of being able to compose and things like that. Okay, so basically, as far as statistics goes, the whole idea of statistics is that we want to make inferences. We want to look at a sample and make conclusions about the population based on what we see in that sample. And kind of a key idea there is when we see something in a sample, right? We notice some kind of phenomenon happening in the sample. We want to be able to distinguish between, is what we're seeing a random fluke? Could this just be the result of random effects? Or is this actually an indication that, there's something interesting actually happening, right? And so how are we supposed to distinguish between what's happening randomly versus what's actually happening? And in order to understand that, we need to understand randomness. And basically, probability is all about understanding randomness, okay? And so, I don't know, do we have any fans of board games, fans of Settlers of Catan or something like that? Okay, all right, thanks for the head nod and the hands up there. Okay, so in Settlers of Catan, you roll dice. Okay, you roll these 2 dice, and one of the things is that when you roll a 7, you can take this little robber, and he's gonna, or the barbarian, and he's gonna go and steal goods and materials, resources from an opponent and things like that, right? And sometimes the barbarian is attacking your land and you're just waiting for the 7 to roll and it doesn't roll for a very long time or things like that. Right? These are frustrating things that can happen in the game. And so, if you look at the outcomes and the rules of probability, the probability of rolling 2 dice where the total adds up to 7 is 1/6. This should happen 1/6 of the time, right? And so let's say, here I've got these 2 large dice. These are like the toys of a statistician, right? So you throw your dice, and let's say you've been you keep track of all of the dice throws that happen in a game, right? And you say, all right, we ended up throwing the dice 72 times so far, and look at this. The number 7 showed up 18 times out of 72, right? And you say, if these were fair dice, where the number 7 shows up with probability 1 out of 6, okay? With 72 throws, it should show up 1/6 of the time. I should only get 12 number 7s, okay? Now what happened to me? I got 18 number 7s, right? Is this just randomness, right? Could you throw fair dice and end up getting 18 random 7s, or is like something wrong with your dice, right? Should you go and replace the dice because something is wrong with the dice that have been included in your board game, and the dice that have been included, somehow they're unfair and they're landing on the number 7 more often, right? I don't know if you've ever had that thought, right? When you're playing, you're just like, man, something's wrong with these dice. We got to get some new dice. And so basically that's a question we can ask and try to answer with statistics. And the answer depends on probability, right? Maybe if we understand probability, we can say, oh, you know what? Getting 18 7s out of 72 throws, not that weird. Or maybe the rules of probability say, hey, yeah, 18 7s out of 72 throws, that shouldn't really ever happen. And if that happens, that means something's wrong with your dice, right? We want to be able to distinguish between those kinds of possibilities here, okay? So we're going to learn about the rules of probability, okay? And so probability expresses how likely or unlikely some particular outcome is, right? How likely is it that we get a 7 when we roll 2 dice or something like that, right? And it's worth noting that there's a couple notions of probability. We've got theoretic probabilities and we have empirical probabilities, okay? The focus of our class is mostly going to be on theoretic probabilities. Theoretic probabilities are long run relative frequencies, okay? Long run, this is why it's theoretic, means the number of trials approaches infinity, right? And obviously we can't ever really approach infinity in real life. And that's why it's kind of this theoretical idea. It's just like, if we could theoretically do something an infinite number of times, what's the relative proportion or what's the relative frequency that we would see, okay? And to kind of get those answers, we use mathematical rules for finding these theoretic probabilities, right? So we could talk about flipping a coin. And, this is like one of your most basic ideas of a theoretic probability that I think, even young children understand, is that, yeah, you've got a coin, you have 2 sides to the coin, and each side has an equal chance of landing, right? You got an equal chance of landing heads, equal chance of landing tails. And because there's 2 sides, therefore the probability it's going to land on, say heads, one of those sides, is going to be 1 out of 2, right? And so the probability that a coin lands heads is 1/2, right? And that's a theoretic probability, okay? And empirical probability, on the other hand, these are estimates of probability, estimates, and they are based on actual observations from a real life experiment, or perhaps even a simulation or something. And we have to oftentimes resort to empirical probabilities because the math to find the theoretic probability just doesn't exist in real life, right? Or just doesn't exist, right? So a silly example, right? You've never seen a coin before. Let's say you're an alien, you've never seen a coin before, and you don't quite understand the rules of physics on Earth. So you say, well, it does seem that people use this for because of the random outcomes. And so you flip it, say 50 times, and out of 50 times it lands heads 23 times out of 50. And so the estimate of how often do we get heads is going to be something like 23 out of 50. And we're going to say, based on the 50 outcomes in the past, we got heads 23 out of 50, 46% of the time. Therefore, I'm going to estimate that, this random outcome results in heads something around 46% of the time. Now, that's silly to do something like that for a coin flip, but this is pretty much how we have to estimate probabilities for any kind of medical treatment, right? How effective is the coronavirus vaccine, okay? How effective is that? You can't look at the materials that go into the vaccine and just say, oh, mathematically, this is the answer, okay? We don't have that, right? So what happens is you give it to a whole bunch of people, and then you look at the results, and based on the results, you get an estimate, right? So, something else we could just say, what's the probability that, some certain medical treatment for a particular patient will be successful, right? So, you say, I suggest using this medication or something, right? And you look at that treatment and you look at kind of the history, right? You say that, this medical treatment has been performed or given to other patients with the same, physical ailment or condition. And perhaps you look at similar background demographics, maybe in the same age group and gender. And you'll say, when we gave this treatment to other patients with the similar condition and similar background, it was successful 80 times out of 100 cases, right? And so that's based on real data. And then you'd say, okay, our estimate of the probability of success for you is going to be 0.8, okay? Because it was successful in 80 times out of 100. Just because there's no math where you can just kind of plug in, oh, how old is somebody? Oh, this person is this old, and and therefore the answer is going to be this. We just kind of have to guess. And this is why as far as medical treatments and experiments and things like that go, it's very important that we get a wide diversity of participants, just because something that could be effective for one age group or one gender or one ethnic or racial group, just because there's a certain probability of success here, doesn't necessarily mean it's going to have the same effect for people in other demographic groups, okay? And so, we can look at a lot of times, you will see studies that were performed in another country, studies that were performed in China or India or some European country, and the results there may or may not necessarily hold true for, people in the United States, just because there are not just differences in race and ethnicity, but a lot of other things like diet, right, is going to be different from one nation to another. And those things could play a factor in the outcomes of the patients. And so, when you use empirical probabilities based off of real life data, we want to be aware of just kind of, does the sample of people, that we're looking at these results, is that representative of the group that we're trying to generalize to? And if the answer is it's not representative, we just have to be careful, right? So anyway, these two things, the theoretic and the empirical, have a meeting point at some place in the idealized hypothetical world, right? So theoretic probabilities are based on long-run relative frequencies. If we could repeatedly roll the die an infinite number of times, we would get the theoretic probabilities. And the empirical probabilities are also based on relative frequencies, but they're based on relative frequencies from actual observations or simulations and things like that. And the idea here is that as you perform more and more real life trials, more and more actual experiments or things in real life, the observed relative frequency, the thing that you get your empirical probability, will approach the theoretic probability. And this is what we call the law of large numbers, okay? And that's basically what keeps casinos and insurance companies in business. So I don't know if any of you are old enough to gamble or have been to Vegas and have played any of the table games or slot machines or something like that. But basically, all of those games are designed in such a way that the casino maintains a probabilistic advantage, right? That more often the casino, theoretically, more often the casino will win money than lose money, okay? But the reason why casinos are able to stay in business is because there's random chance, and therefore, when somebody plays, sometimes that player will actually win and the casino will lose money, okay? Because if the whole business of the casino was the casino always wins, every single game the casino wins, players will not go to the casino. They will say, oh, I will just lose money, okay? But the games are designed so that sometimes the casino wins and sometimes the player wins. And because sometimes the player wins, people come back and they keep playing. And so the casino actually wants to occasionally lose money to the players because that will make the players more willing to continue playing the game. And they also know that because of the law of large numbers, the more times people play over the course of, of a day or a month or whatever, with hundreds of people playing, thousands of people playing, overall, the law of large numbers will just win out, and therefore the casino will make more money in the long run, okay? Same thing with insurance companies, but just the opposite. In the insurance companies, they design their premiums, the premiums that they calculate that you have to pay each month, they are set up in such a way that they expect to earn more in premiums than they have to pay out in claims. And the ideal insurance customer is the customer who pays their premium, maybe a very low premium, but never gets in a car accident or something, right? Never get in a car accident. The insurance company never actually ever has to pay out a claim, and they just gets to keep all of the monthly premiums that they charge. All right, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter B. B as in bear. B as in bear is the first view quiz answer for today. All right, so let's get into kind of notation and the mathematical stuff that goes into probability. So these are kind of the basics. So we're going to say there's some event. We're going to just call the event A, and the probability that event A happens is written as PR of A, sometimes just P of A, okay? So these are kind of similar two ways of writing the same thing. Probability of A is going to be written this way, okay? And so if we say event A is the event that the coin lands heads, we can write something like this. We can say the probability of A, probability that the coin lands heads is equal to 0.5, okay? We can also write something like this. Probability of heads is equal to 1/2, all right? Now, one thing that's important is A is equal to, do not say A equals 0.5, okay? A is the event. A is the event, okay? A is not, the event is not 0.5, okay? The event is that the coin lands heads. The probability of the event is 0.5. The event itself is not 0.5. It's the probability that's 0.5, right? So we can say the probability of A is 0.5. Don't say A is 0.5. A is the event that the coin lands heads. So there is a distinction there. Okay. Oh, a question in the chat. Yeah. The first view quiz answer is the letter B. First view quiz answer is the letter B. You know, if for whatever reason you mishear something in during lecture, don't hesitate to just ask again in the chat. No worries. Okay, but but at the end of lecture, don't just say, hey, what were all three view quiz answers? I'm not willing to do that, but just do it within a couple minutes of you missing it or something. No problem there. Okay. So yeah, first view quiz answer, the letter B. Okay. So all probabilities are a value between 0 and 1. Okay, all probabilities are a value between 0 and 1. So we can just write it also like this. 0 is less than or equal to the probability of some event X less than or equal to 1. Probabilities can be expressed as fractions, decimals, or percentages, and I use these things interchangeably. And so oftentimes when you see something, if it says 0.5, I might just say 50% or 1/2 or something like that, right? And I hope we're all comfortable enough with decimals and percentages that's not going to be confusing. All right. If the probability of an event is 0, it means that event is never going to happen, right? That event is impossible, okay? And if the probability of an event is 1, it means that thing is definitely going to happen. It is certain to happen, is what we say, okay? Maybe there is a there is a subtle distinction between probability 0 and absolutely impossible, but I don't want to get into it, okay? But for all intents and purposes, we can just say probability 0 means impossible. It's never going to happen. Okay. So the complement of some event, the complement of some event A is the outcome that event A does not happen. Okay. So if you got some event A, the complement is when A doesn't happen. And we write that as AC or just plain old not A, okay? If A is the outcome that the coin toss lands heads, the complement is the outcome that the coin toss does not land heads, okay? And so technically that would include all possible outcomes where the coin doesn't land heads, such as the coin rolls away or the coin lands on its side, or, you know, in addition to just the coin landing tails, okay? But for simplicity, we can just say, you know what, A complement means the coin lands tails, right? And we're just going to ignore anything else. We're going to ignore the possibility that the coin lands on its side or something like that, right? And so if, so anyway, if we have event A, the complement of A has the probability of 1 minus the probability of A, right? So the probability of A complement is equal to 1 minus the probability of A. And that makes sense because if you got a 80% chance that something happens, you're gonna have a 20% chance that it doesn't happen, right? Basically, you just do 1 minus that thing. We have in some cases, in some situations, you're gonna have different outcomes, and those outcomes are equally likely. This is not all scenarios, okay? But in some scenarios, you've got outcomes and all the outcomes are equally likely. And event A could be made up of several of these equally likely outcomes, okay? The probability of something like this, right? You got event A made up of several of these outcomes. The probability can be found as the number of outcomes included in event A and divided by the number of all possible outcomes. So let's just take a simple example here, right? We've got a, let's say I've got this cup of M&M candies, okay? And you don't have anything better to do, so you counted them all out. There's 168 pieces of candy total. 30 of them are brown, 25 are red, 20, we list them off, right? Every single color and every single possible, the count of each of these things: 28 orange, 26 yellow, 32 green, 27 blue, okay? And what we're gonna do is we're gonna shake up the cup and we close our eyes, we pull out a piece of candy. All right, we're gonna say, what's the probability that this piece of candy that you pull out is a brown M&M, okay? Well, we're going to say all 168 pieces have an equal chance of being selected. Of those, 30 of them are brown, and therefore the answer is going to be 30 divided by 168, okay? And that's something like 18%, 17.86, 0.1786, okay? I don't think that's a surprise for anybody, right? That's simple, okay? And then if we ask, okay, well, what's the probability that you get a piece of candy that's not brown, Okay, well, you just do 1 minus the probability of Brown. So probability of Brown is 30 over 168. 1 minus that, okay? So that would be what, 138 over 168, or 82%, something around there. So far, so good? Great, okay. All right, and so here is a table. This is what we actually call a two-way table, because we're looking at two variables here. One is whether students are first year, second year, third year, fourth year in school. And we're going to say, whether the student is from California or not from California. I completely made up this information. And so we're going to say we got 208 students. And this is kind of the breakdown. And so what we're going to say is we're going to select a person at random from the table. Okay. And so we're going to assume that all 208 people in our table have an equal probability of being selected. Okay. And we're going to say, we're going to ask, what is the probability that the random person we select is going to be from California and a first-year student? Okay. All right. What do you guys think? And this is, I think, pretty easy. You can just type a number into the chat. You can just type in a fraction. You don't even have to do a computation. All right, there we go. 40 out of, all right, okay, everybody's typing in the answer, right? 40 out of 208. Okay, simple enough, right? We just say, all right, well, how many people are from California and first-year students? We have 40 people, okay? And we got a whole bunch of other people as well, but 40 people fit that description of being from California and a first-year student. So our answer of this is going to be 40 divided by 208, something around 19% if you do the computation. Okay. We can ask or, okay, A or B. And in statistics and probability and in our class, the or is always an inclusive or. There is a ambiguity in the English language, and actually a lot of languages mostly, is that that we only have the one word for or, and sometimes it's exclusive or, and sometimes it's inclusive or, right? So the difference between inclusive and exclusive or, basically I could ask you, do you like, I guess it depends on the context, right? But I could ask the same question, right? Do you like chocolate or vanilla ice cream? And depending on the context, your answer is either going to be yes, or your answer is going to be, I prefer, chocolate ice cream, right? So it could be, what do you have for dessert? Let me check the freezer. Oh, hey, do you like chocolate or vanilla ice cream? And the answer is going to be, oh yeah, that's good. Yes, I like that. That's good. Okay. Or maybe in the other context, you go to the ice cream shop and you have to make a choice about what kind of ice cream you're going to get. And so you say, hey, do you like chocolate or vanilla ice cream? Same words, different context. And in that case, you're going to say, oh, please get me the chocolate one, or please get me the vanilla one, right? So the one where you just say either yes or no, that's the inclusive or, meaning either A or B or both is good, okay? And then the other one is where you make one choice but not the other. That's the exclusive or, okay? As far as probability goes, it's always the inclusive or, okay? Meaning when we say A or B, we're talking about A or B or both, right? Okay, so in this question, we got 208 people. And now the question is, what is the probability that the person is from California or is a first-year student, meaning California or a first year or both, right? If you're ready to give me an answer in the chat, you can just type in a number in the chat. Again, as a fraction is fine. Okay. All right. A lot of you are getting it right. 150 out of 208. And yeah, that's the answer, right? So we're going to look at all the people who are from California or a first year or both, right? And so we can say, okay, we got all of these people. These are all the people from California. We got the first year Californian, second year from California, third year from California, fourth year from California. We add all of those up. Those add up to 120. We also add up this number. we have 30 first-year students who are not from California. They also count as being from California or being a first-year student or both. And so when you add those up, you get 150 out of 208, okay? 150 out of 208, and you get something around 72%, right? So we can just kind of take all of these numbers of people who qualify, and we get 150. Another way we could look at it is to use this formula that the probability of A or B is equal to the probability of A plus the probability of B minus any overlap. And so here's the picture, the diagram here, the Venn diagram. This circle represents A, this circle over here represents B. And so the probability of A is this circle, which is consists of the blue and green parts. Probability of B is this circle, which consists of the yellow and green parts. But if we add these two together, we have double counted the green. So we want to subtract off, the overlap here. We're going to subtract off this overlap between A and B. Okay, so we could take that approach. We're going to get the exact same answer, but we can just look at the total. We can say, okay, how many people from California? 120. What's the probability of coming from California? 120 out of 208. What's the probability of being a first-year student? 70 out of 208. Okay, and if we add those two up, we get 190. But this 120 consists of these numbers. This 70 consists of this number and this number. And so we're double counting this 40, right? So we gotta subtract that off. Okay. So we do, 120 plus 70. We subtract off the overlap one time, and we would get the same answer, 150 out of 208. Okay. So two approaches to get to the same answer. And it looks like a lot of you, I know the people who choose to participate in the chat are the people who are with it and are getting it. And not everybody's participating in the chat, and that's fine. I'm not expecting everybody to, but I just kind of want to make sure that everybody else is okay as well. And again, if you have any questions, don't hesitate, okay? Don't hesitate to ask. I'm sure there are other students who have the same question as you. Okay, if we have events that are mutually exclusive, what that means is that these two events cannot happen together, okay? If event A and event B are said to be mutually exclusive, then that means the probability of A and B is equal to 0, meaning that you cannot, if A happens, then B at the same time cannot also happen, or if B happens, then A at the same time cannot happen. These things are mutually exclusive. And so if that's the case, when somebody says, what's the probability of A or B? There's no overlap to worry about anymore, right? So when you say, what's the probability of A or B? This is the answer that we apply, probability of A plus probability of B minus the overlap. But in the case of a mutually exclusive event, so this overlap is 0. So you can just do the probability of A plus the probability of B, okay? If you know the events are mutually exclusive, we know that that we can ignore this part because this part is 0, okay? So for example, if we look at this thing and we say, what's the probability that a person is a first-year student or a second-year student, okay? And we're gonna assume, this is the assumption. I know at UCLA we have like people are like, oh, I'm a first year, but I got second year standing. Okay, we're gonna just ignore all of those cases and things like that, okay? Or we're just gonna say, this is either your first year on campus or your second year on campus or something like that, or whatever, your first year of enrollment, we should say, because perhaps a lot of you haven't even set foot on campus. So we'll say, your first year or second year of enrollment in classes and things like that. So either you are a first year or you are a second year. You cannot be both, okay? And so therefore, when we say, what is the probability that a student is a first year student or a second year student, okay? It's first year or second year or both, but there is no both. No student is both a first year and a second year simultaneously. So all we have to do is we just add the 70 out of 208, the 95 out of 208. There's no overlap to subtract, and therefore we just get 165 out of 208. Okay, and that's it. Okay, So they're mutually exclusive. We don't have to worry about subtracting the overlap. And that's going to come in handy because later on we're going to ask, what's the probability of this thing or this thing happening? And you don't want to have to try to calculate the overlap, but you don't have to, because it turns out, if you think about it, there's no overlap for you to worry about. Okay. When we're talking about and or, the order of the events inside the parentheses, they don't matter. So when you talk about, what's the probability of A and B, that's going to be the exact same thing as the probability of B and A. What's the probability of A or B? It's the same thing as the probability of B or A. So we don't have to worry about, swapping these things and changing the values. Okay. Once we've established those rules of conditional probability, basic probability rules, now we can talk about conditional probabilities, and this is going to be important. Okay. Here is possibly something new for you, maybe not. You might see a probability with a vertical bar written here. Okay. This vertical bar means given. This is the conditional probability of A given B. Okay. This is the probability of event A happening. What is the probability that event A happens given the fact that B happens, right? So this is a silly example that just plays on stereotypes of maybe two states in the country. We've got California and we have Texas, and so I'm just, hopefully these are just playful stereotypes of each of our states here. And the question is, what's the probability that somebody drives a pickup truck, right? So you're thinking of like the F-150 or the Silverado or something, whatever, right? And so if you think about California, think about Texas, the stereotype is that, in Texas, you got a bunch of cowboys and a bunch of people driving trucks and things like that. And so we would say, we have the probability that someone drives a truck or pickup truck if they're from California, given the fact that the person is from California. So this is probability of drives truck given California is the probability that someone drives a truck if we're given the fact that the person's from California. And over here, we've got the probability that someone drives a truck given the fact that the person is from Texas. Okay. And so if we play off of the stereotypes, we would assume, we would say that the probability that someone drives a truck is going to be higher if the person's from Texas versus the person being from California, right? And this could change it, what's the probability that someone drives a Tesla or something, right? Okay. And then some, in California, we've got, again, the playful stereotypes. California, we've got a bunch of Teslas and Priuses, and then Texas, they've got a bunch of pickup trucks and stuff like that. Okay, is that all right? Does that kind of make sense? This idea of a conditional probability. All right, and so the way we calculate this is that the probability of A given B is going to be found by taking the probability of A and B divided by the probability of B. Okay, and if you have a table, like a two-way table where you have all of these counts and things like that, you can just also do the count of A and B divided by the count of B. Okay. And one thing to note is that when you do conditional probabilities, you cannot just switch them, right? So a couple slides ago, I said probability of A and B is the same thing as the probability of B and A. That's true. You can switch the order there. But as for conditional probabilities, you cannot. The probability of A given B is not going to be the same thing as the probability of B given A. Okay. Maybe in some certain situations by coincidence, they might happen to be equal, but in general, the probability of A given B is not going to equal the probability of B given A. All right, so again, making up some arbitrary data, talking about trucks and people not driving trucks and people from California versus Texas. This is what our table looks like here. And so if I ask the question, give me the fraction or to represent the probability, right? So we're going to say, what is the probability? We pick a person at random from the table, and we're going to say, what's the probability that this randomly selected person drives a truck given the fact that they are from Texas, right? So we're going to say, what's the probability that someone drives a truck given that they're from Texas? Okay, and what would you guys say? Go ahead and if you feel like entering a fraction into the chat, what would you say? Probability that someone drives a truck, given that they're from Texas. Yeah, okay. A lot of you guys are entering it in the chat, and you guys are absolutely right. Okay, we're going to say, okay, how many people are from Texas? 1170. We're going to put 1170 in the denominator. And of those, how many drive a truck? 420. So our answer is going to be 420 out of 1170, 0.359. Okay. Okay. What is the probability? And so here's the question is phrased a little bit differently. What's the probability that a randomly selected person from California drives a truck? Okay. And this answer is going to be the way we would formulate this given probability is the same. Probability of truck given California, right? What's the probability that a randomly selected person from California? So now the question is phrased differently. The given part comes first. It says, because it establishes that we are looking at people selected from California. And the question is, what's the probability that this person drives a truck? So we're still asking, what's the probability of truck given California? All right, and so our answer here is going to be 470 out of 1575, something around 29, 30% here, okay? All right, and this one phrased a little bit differently. We're going to ask, what is the probability that a randomly selected person is from Texas if we know they drive a truck, right? So with this being phrased this way, the piece of information that is given to us, the piece of information that we know is going to be that we know they drive a truck, okay? So here, the given part is that they drive a truck, and we're asking what's the probability that the person is from Texas. So here, it's going to be the probability that someone's from Texas given truck, right? Is that okay? I want to make sure that we can distinguish between this probability of truck given Texas versus probability of Texas given truck, because the answers are going to be very different, right? So what's the fraction that we would use? And again, if you want to enter it into the chat, what's the fraction we would use for probability of Texas given truck? Okay, all right, great. A lot of you guys are entering it in the chat, so that's great. Yes, 420 out of 890, right? So the piece of information we know is that they drive a truck, and of those 420 are from Texas, okay? And again, just to kind of emphasize, like A given B is not the same as B given A, we can see that these answers are different, okay? We got 0.359 versus 0.471. And then, is there a difference, do people from Texas drive trucks at a higher probability than people from California? And the answer is yes, right? We got around 30, according to my arbitrary table that I made up, okay? So please don't use this as some reputable source. I just made up these numbers. According to our table, around 36% of people from Texas drive a truck, where in California, maybe only around 30% of people drive a truck, okay? Okay, I'm gonna just kind of skip through these real fast, just in the interest of time. What's the probability that a randomly selected person drives a truck and is from Texas? Okay, so that's just an and question. So we're going to say drives a truck and from Texas, 420 in the numerator. In the denominator, it's just a random person from the table. So we're going to just do 2745. So truck in Texas, 420 out of 2745. What's the probability that a randomly selected person drives a truck or is from Texas? So we're going to look at everybody who drives a truck plus everybody who's from Texas. Subtract off the overlap. We're going to get, 890 plus 1170 minus 420. Everything over 2745, we get something around 60%. And here, what's the probability that a randomly person is from Texas or from California? At least in our table, these things are mutually exclusive, and we just add these two things up and we get a probability of 1. Okay. If we play around with a little bit of algebra, we can arrange the rules or this probability formula, and we can get something known as Bayes' rule, okay? So a couple slides ago, we said this is the definition of this conditional probability. The probability of A given B is equal to the probability of A and B divided by the probability of B, right? So just with a little bit of algebra, I'm going to rearrange things. Multiply probability of B to both sides. We're going to get the probability of B multiplied by the probability of A given B. This is equal to the probability of A and B, okay? And you could imagine just kind of swapping the letters B and A. Probability of B and A can also be written this way: probability of A times the probability of B given A. And so if we set these two things equal to each other, I can also solve for the probability of A given B by taking the probability of A times the probability of B given A and divide by the probability of B. And this thing is known as Bayes' rule. Probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. Okay, this is a bunch of letters and a bunch of probabilities and a bunch of this and that, blah, 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 blah. It probably doesn't make a whole lot of sense just yet. And so what we will do is we will do an example, and I hope that will make a little bit more sense, okay? Okay, before we get into this example here, let me go ahead and give you your second view quiz answer. Second view quiz answer for today is the letter E. E as in elephant. E as in elephant is your second view quiz answer today, okay? E as an elephant. All right, second view quiz answer. Okay, can I show the Bayes' rule equation again? Yes, it's this, and that's what we have, and we'll do an example here, okay? And don't worry, I'll write it up when we do the example. So let me bring my notes here. Okay, so this is just an imaginary scenario here. And so we're going to say we go to the airport. You're going to get on an airplane. And we're going to say if there's a storm, your flight might be delayed. And if there is a storm, we're going to say the probability that your flight gets delayed is 60%, 0.6. Okay, so the probability of a delay, if there's a storm, is going to be 0.6. Okay. If there's no storm, sometimes your flight still gets delayed, right? So if there's no storm, the probability of a delayed flight you can still get delayed, and it's going to happen with a probability of 7%. So the probability of delay given no storm is only 7%. Okay. And we're going to say the weather forecast says the probability of a storm is 25%. Here, let me okay. So the probability of a storm is 25%. And the question is, what is the probability that there's a storm and the flight also gets delayed? What's the probability that there's a storm and the flight gets delayed? Oh, oops, sorry. Okay, so let me just write this. So we're going to write probability of delay given storm, 0.6. Probability of a delay, even if there's no storm, given no storm, 7%. And we're going to say the probability of a storm is 0.25. Okay. And so the formula we're going to use here is the probability of A and B is equal to the probability of A times the probability of B given A. Okay. So we're going to say, the question is, what is the probability that there's a storm and your flight gets delayed? Right. So what's the probability there's a storm and the flight also gets delayed? So we're going to ask, what's the probability of a storm and a delay? And so this is going to be the probability. We're going to say A is the storm. So this is going to be the probability of a storm times the probability of B given A. This is going to be the probability of a delay given a storm. Okay. And we have the probability of a storm is right here, 25%. And we'll multiply that the probability of delay given a storm, 60%. Okay, we multiply these two together. 15%. Storm and delay, 15%. Okay. Is that all right? Great. Okay, now, if you made a mistake, and it's not hardly a mistake, right? Like, what if you wrote it this way? Probability of delay and storm, and you tried to do it this way. And you tried to do probability of delay multiplied by the probability of storm given delay. Okay, this is equally valid, okay? Except you'd be like, oh, what's the probability of the delay? And that information doesn't exist here in this table, okay? And what's the probability of storm given delay? That information also doesn't exist, right? So, you'll get stuck, right? So if you happen to write kind of, switch delay and storm, and you write it this way, you'll just kind of get stuck because you won't have a number to put here for probability of delay and something, right? Okay, we have a question that says, can you explain the equation you got first, how you got the probability of A and B? Oh, this thing, probability of A and B equal to this, that's just one of the definitions. That's, where is it? Oh, okay, it's right here. Probability of A and B is equal to the probability of B times the probability of A given B, or the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so this is just from an earlier slide. Is that okay? All right, so what is the, okay, what's the probability that there's a storm and the flight also gets delayed, storm and delay, and this is the answer that I've done here, okay? All right, let's ask this question. What's the probability that the flight is just delayed in general, okay? What's the probability that the flight just gets delayed in general? So I'm gonna go ahead and I'm gonna just copy. Oh, shoot, I can't do it. Okay, let me just create a new slide here. All right, so we've got probability of delay given storm, 0.6, probability of delay given no storm, 0.7, and the probability of a storm is 0.25. Okay, and so the question is, what's the probability of the flight is delayed? So the question is asking, what is the probability of a delay? Okay. All right, and so the way we're going to answer this is we're going to build something called a probability tree. Okay. And basically, I'm going to take these branches, and we're going to say, what we want to know is what's the probability of delay. So we're going to put either there's a storm or no storm. And then along this side, we're going to put in the probability of a storm. What's the probability that there's a storm? 0.25. This is the probability of a storm. 0.25. Okay. So if there's a 25% probability of a storm, what's the probability of no storm? Okay. 0.75, right? 25% probability of a storm. So that means probability of no storm is 0.75. Okay. And then if there's a storm, we can either experience delay or no delay. Okay. So if there is a storm, what's the probability I have a delay? What number do I put here? If there is a storm, the probability we experience a delay is going to be 0.6. Yep. And so this value is the probability of delay given storm. Okay. So then what number should go on this side of the branch? We got 60% up here. What are we going to put here? We're going to put exactly, we're going to put 40% down here. So this is the probability of no delay given storm. Okay. All right. so over here, I will also write out my branches. I've got delay versus no delay. If there's no storm, we can still be delayed. That happens with a probability of 7%. This is the probability of a delay given no storm. And then I got 7% here, so I'm going to put 93% down here. And this is going to be the probability of no delay given no storm. All right. And okay, so then what we do is we just multiply our numbers down the branches. Okay, so I'm going to do 0.25 times 0.6. This gives me 0.15. And this is going to be the probability of a storm and delay. All right, and that was my first question. What was the probability of a storm and a delay? That was the question we answered on the last slide. Here I'm going to do 0.25 times 0.4. I get 0.1. And this is the probability of storm and no delay. 0.75 times 0.07. I don't know. I don't remember what that was. Let me pull up my calculator. 0.75 times 0.07. 0.0525. This is the probability of no storm and a delay. And then the last one, 0.75 times 0.93. This is going to be 0.6975, I believe. If I did this correctly, 0.75, yep, 0.6975. And this is going to be the probability of no storm and no delay. Okay, we still don't have our answer to the question of what's the probability of a delay. So the probability of delay happens if we end up here or we end up here. Okay, so where can I write this? I'm going to write the probability of a delay is going to equal this number, probability of a storm and a delay. So there's two ways we end up being delayed, right? There's a storm and we get delayed, or there's no storm and we still end up getting delayed. And these events are mutually exclusive, right? There's no scenario in the world where you can experience a storm and a delay, and at the same time you experienced no storm and a delay, right? Either there's a storm or there's not. You're not going to have a simultaneous thing. So all we're going to do is we're just going to add these two things together. There's no overlap for us to worry about. So the probability of storm and delay, 0.15. The probability of no storm and still we get delayed is 0.0525, and this adds up to 0.2025. Okay, and that's our answer here. So what is the probability that we get a delay? .2025. We're good there? Give me a thumbs up if you're good there. Great. Okay. Appreciate it. Okay, so the answer is, so I wrote, here's kind of the slide here, and also formula right here, okay? To kind of get the answer, 0.2025. The other question is, you go to the airport to pick up your friend. So we're going to pretend that this is the age before cell phones, or you don't have your cell phone with you or something, right? So you go to your friend, you go to the airport to pick up your friend. You look at the board and it says the flight was delayed, right? Now, you know, the adventure of going to the airport It's no longer an adventure. You just check on your phone and you can see exactly where the airplane is, and you know exactly whether it's going to be delayed or not. But we're going to pretend that we live in the 60s or something, and you go to the airport, you see the thing and it says, oh, the flight's delayed. Okay. And then you go, oh, I wonder if there was a storm. Okay. And this is a contrived scenario, but that's where we are. We go, oh, I wonder if there was a storm. And so so now we want to know, okay, given that there's a delay, what's the probability that there's a storm? Okay. So that's going to be kind of the flip side, right? So given that there is a delay, what's the probability of a storm? So we're going to ask, what's the probability of a storm given the fact that we know there was a delay? Okay, we're going to use the same tree diagram here. And here, the probability of storm given delay, we're going to just use the definition of, conditional probability. This is going to be storm and delay. And what do I divide by in the denominator? We're going to divide by the probability of a delay, right? Because the definition for a conditional probability, sorry, this slide is a bit of a mess, but A given B is equal to the probability of A and B divided by the probability of B. Okay, so this is just the definition. This is just on an earlier slide. And here, we're going to say the probability of storm given delay is going to be storm and delay divided by the probability of delay. Okay, and so basically, once we know that the flight has been delayed, in the denominator, we're going to put in the probability of delay, which we calculated on the previous, we calculated earlier. Our previous problem was, what's the probability of a delay? So we're going to put 2025 in the denominator. Okay, and what value goes in the numerator? Probability of a storm and delay, that's going to go in the numerator. So we're going to put this number, 0.15 in the numerator. Okay, and then you do some math here. And by math, I just mean type numbers into a calculator. Okay, and 0.15 divided by 0.2025, I get 0.741. All right, yeah, if I round off to 3 decimal, 0.740740740, okay? And yeah, and that's good enough. Okay, probability. All right, so if you find out that the flight was delayed, what was the probability that there was a storm? Something around 74%. Something around 74%. Okay. Any questions there? I feel good. So so that's what we have here. 0.741, and there's our answer. Delay and storm, et cetera, et cetera. Okay. I'm going to keep moving unless somebody has a question here. If okay, let's talk about independent events. All right, so we're talking about conditional probabilities, and now we can talk about independent events. And the idea is, if events are independent, the outcome of one event is not associated with the outcome of the other event, right? So if two events are independent, the outcome of one is not associated with the outcome of the other, right? So if you have events A and B, and we say these two events, A and B, are independent, what that means is that the probability of A given B is the same as the probability of A given not B. So whether B has happened or hasn't happened, the probability of A happening is just the probability of A. The probability of A, if B has happened, is not influenced, is no different than the probability of A happening if B hasn't happened, right? So the probability of A given B has or has not happened is just the same, okay? So the probability of A given B is just the probability of A. The probability of A happening is not affected by whether B has happened or has not happened, right? Event B has no influence on the outcome of A. That's what it means for things to be independent. You're going to see this relationship. Probability of A given B is the same as the probability of A given not B. Okay. And if A is independent of B, then that means B is independent of A, right? And kind of the flip side of that is also true. If B is not independent, okay, meaning that it's dependent on A or of A, then A is not going to be independent of B, okay? So if B is not independent of A, then A is not independent of B. All right, so what do you guys think? Is driving a truck independent of being from Texas? Being from Texas versus California, what do you guys think? Is driving a truck independent of being from Texas? Yes or no? What do you guys think? Before we even do the math. Okay, so a lot of people are saying yes, but the actual answer is no, that they are not independent, okay? And that's okay, don't, this is why we have class, right? So if you feel like, what do you mean they're not independent? Like, what does being from Texas have to do with driving a truck, right? So the idea of if they are independent, whether someone is from Texas or not from Texas is going to have no influence on whether or not they drive a truck, okay? And according to our table, what we find is that, okay, what's the probability that someone drives a truck if we know they're from Texas versus what's the probability that they drive a truck if we know that they're not from Texas? What we find out is that if we know somebody is from Texas, then the probability that they drive a truck is a higher number, okay? If we know that the person's from Texas, we're gonna say that, that there's a higher probability that they drive a truck than if they're not from Texas, okay? And so the fact that the probability that they drive a truck actually is influenced or changes, I don't know what the right word is, but it's basically different for people from Texas versus people who aren't from Texas, okay? Because that number is different, they are not independent, okay? Meaning that knowing whether somebody is from Texas or not from Texas will affect whether we believe this person drives a truck or not, okay? Right, so if I say, hey, if we pick a random person and we say, hey, do you think this person drives a truck? They might say, I don't know. How am I supposed to know? Okay, how am I supposed to know if they drive a truck, right? And maybe I'll just tell you, the national average for people who drive trucks is like 1 in 3, 33%. Okay, great. That would be my guess, right? But then we say, oh, just by the way, this person's from Texas. You go, oh, they're from Texas, then I think there's a higher probability that they drive a truck or something like that, right? And so the fact that knowing that the person's from Texas would kind of influence the probability, and influence is perhaps not the best word to use because that implies like a cause and effect relationship. And we're not just saying that like somehow the land of Texas causes people to drive trucks or something, but just the fact that there is a difference in the probability indicates that they are not independent, right? People from California and people from Texas have different probabilities of driving a truck. So therefore, driving a truck or owning a pickup truck is not independent of being from Texas. Is that okay? That the answer here is no, that they are not independent. They are not independent, or we could say they are dependent, okay? All right, so let's try this one out, okay? Is being left-handed independent of wearing glasses? Is being left-handed independent of wearing glasses? Okay, so how would we go about, this is, let me shrink this little work area here, okay? So how would we go about answering something like this? What did I do? I just lost my pen. Oh, okay. It's right in front of me, just being dumb. Okay. Okay, so what we want to know is being left-handed independent of wearing glasses, and this is what my data looks like, right? So if two events are independent, right? So if A and B are independent, okay, then we can say that the probability of A given B is going to be equal to the probability of A given not B. All right. So what we're going to do is we're going to ask, okay, is the probability that someone is left-handed, and I'm going to just abbreviate it LH, given glasses, is that equal to, so we're asking a question, is that equal to the probability that somebody is left-handed given that they do not wear glasses? Okay. And if they are equal, they are independent. If the two values are equal, they are independent. And if they are not equal, they are not independent. Okay, so what's the probability that somebody is left-handed given the fact that they wear glasses? Okay, so probability of left-handed given glasses. Okay, well, we say, all right, we're going to put left-handed and glasses in the numerator. And in the denominator, we're going to put everybody who wears glasses, 6 out of 60. So this gives me 6 out of 60.1. Okay, and let's check the other. What's the probability that somebody is left-handed given no glasses? Okay, how many people don't wear glasses? 140, that's going to go in our denominator. And how many people are left-handed and don't wear glasses? 14 out of 140. Okay, so here we get also 0.1. Okay, so I get 0.1 is equal to 0.1. They are the same, and therefore the events are independent. Okay, equal, and that means independent. Okay, so we have a question. It says, does it matter if you do left given glasses versus glasses given left? Yeah. Okay, so yes, there are a few things we could check. Okay, and only some of these will satisfy answering our question. All right, so here, I've done the answer work. Left-handed given glasses, 6 out of 60.1. Left-handed given no glasses, 14 out of 140 is 0.1. These two probabilities are equal, and therefore people who wear glasses and do not wear glasses have the same probability of being left-handed. Okay, and we would say wearing glasses and being left-handed are independent. There's a few things we could have checked. Okay, so we checked left-handed given glasses versus left-handed given no glasses. We could also have checked glasses given left-handed, is that equal to probability of glasses given not left-handed? Okay, so I could have also checked that. What's the probability of somebody wearing glasses given that they're left-handed? Probability of glasses given left-handed versus probability of glasses given not left-handed. Okay, and now I'll just kind of do this really quickly here. Okay, so what's the probability that somebody wears glasses if they are left-handed? Okay, so this is going to be 6 out of 20. And so that's 0.3. And then what's the probability that somebody wears glasses given that they are not left-handed? We have 54 divided by 180. Okay, 54 divided by 180 is also going to be 0.3. Okay, 54 over 180. Both of these things are 0.3, and therefore they are equal, so it's okay. So that means they are independent. Okay, so we could have done that. Probability of glasses given left-handed is going to be the same as probability of glasses given not left-handed. Okay, but what you don't want to do, okay, don't do probability of A given B, is that equal to the probability of not A given B or something like that, right? So if you were to do something, or just kind of, so I'll say do not do this, okay, probability of left-handed given glasses versus probability of, say, glasses given left-handed. Okay, these things are not going to equal, and don't do probability of left-handed given glasses versus probability of right-handed given glasses or something like that. Okay, these things aren't going to, don't check this, right? So the front part probability of left-handed given glasses, compare that to probability of left-handed given no glasses. This is an equality to check, or probability of glasses given left-handed, check that against glasses given not left-handed. But don't mix these things up. All right, I hope that now makes sense, and I hope that's okay. All right, so here is a question. I want you guys to think about your answer here, and then we'll go over the solution in a moment. All right, so imagine two events A and B, and we are going to say that these events A and B are mutually exclusive. Okay, events A and event B are mutually exclusive. They both have non-zero probabilities, and the question here is that if you got two events that are mutually exclusive, could these events be independent? Could they be independent? Okay, and so your answer choices are yes, the events are certainly going to be independent, or no, the events are certainly not going to be independent, or the events could be, but are not necessarily independent, right? And so you got, we're going to use the Zoom reactions. We're going to say thumbs up versus clapping versus party hat. It's not really a party hat. What is it? It's a party cone popper, whatever this thing is. What do we call this thing? Okay, so these are your choices. I want you to think about that. A and B, they are mutually exclusive. So think about what it means to be mutually exclusive. And the question is, are they independent? Okay. This is not for points or anything, just it doesn't matter. Okay. Do you guys have your answers ready? What do you guys think? Okay, so we'll go 1, 2, 3, and show me your answers. What do you guys think? Oh, we're quite divided. We got 13, 10, 14, 11, something around there, 7 different. Okay, well, they seem to disappear after a few seconds, but okay. So we had quite a variety of answers there, and that means this is a good question. And so the answer is they are surely not going to be independent. Okay, they are surely not going to be independent. Okay, if two events A and B are mutually exclusive, okay, that means the events cannot happen together, right? If they're mutually exclusive, they cannot happen together. So meaning if B happens, A is impossible, or if A happens, B is impossible, because A and B cannot happen together. That's what it means for A and B to be mutually exclusive, right? Whereas independent means that the outcome of A is not influenced by the outcome of B, that whether B has happened or not happened has no influence on whether A is going to happen. Okay, but that's not the case here, right? If A and B are mutually exclusive, as soon as B happens, then A becomes impossible. Or if A happens, then B becomes impossible. And therefore, if A and B are mutually exclusive, they cannot at the same time be independent. All right, I hope that makes sense. Okay, I'm going to take a risk here. I'm going to go ahead and give you the answer to your third viewing quiz. Third viewing quiz is the letter A as an apple, A as an apple. And I hope you will still stay in the class and not just take off as soon as I give you your third view quiz answer, okay? So your third view quiz answer is A as an apple, okay? All right, let's keep going along here. And we have sequences of independent events, okay? So we've been talking about different things and, conditional probabilities, but now we're gonna say, okay, what if you have independent events? We got event A and event B, and if they're independent, then the probability of A and B is just gonna equal the probability of A times the probability of B, okay? And this can be extended if you have a bunch of events A, B, C, and D, and they're all independent of each other, then the probabilities of A and B and C and D is just going to be the product of the probability of A times the probability of B times the probability of C and times the probability of D, and so on and so forth. If however many events you have, you just kind of take the product, but they all have to be independent of each other, right? So an example is you have this coin, right? You have a coin, and coin flips are independent, right? When you flip a coin and you flip a coin again, each coin flip is independent of the other coin flips. Like what happened in the previous coin flip has no influence on the next coin flip, and so on and so forth, okay? And just to kind of keep this interesting, we're going to pretend I've got a special coin where the probability of landing heads is 0.7 and the probability of landing tails is 0.3, because otherwise we're just going to see 0.5s everywhere. And it could be a little bit odd. So we're going to just say that the probability that the coin lands heads is 0.7. Somehow this is a special coin. The probability that the coin lands tails is going to be 0.3. And what's going to happen? I'm going to flip the coin 2 times. The coin flips are independent of each other. And so this first question is, what is the probability that we get heads on both of my coin flips, right? So each time I flip the coin, I have a probability of 0.7. What's the probability I get heads and heads, okay? Well, we're just going to take the product of these things, right? We just say, well, they're independent. I can just multiply these things together. So to get the probability of heads both times, I wrote all of this out here. Means you have to get heads on the first flip. That's going to happen with probability 0.7. And you have to get heads on the second flip. Okay. Getting heads on the first flip is independent of getting heads on the second flip. So we can just take the product of these two things. We're going to take the product of getting heads on the first flip and multiply it by the probability of getting heads on the second flip. Okay. So what's the probability I get heads on the first flip? 0.7. What's the probability I get heads on the second flip? 0.7. I multiply these two things together and I get 0.49. Okay, so if I have a special coin and I flip it 2 times, what's the probability I get heads both times? 0.49. Okay, 0.7 times 0.7. Okay, I think that's straightforward, right? Okay, let's keep working with this special coin. And, we can just complicate things by asking, just phrasing our questions a little bit weirder, right? So we could say, what's the probability that the outcome of the second flip matches the outcome of the first flip, right? What's the probability that the outcome of the second flip matches the outcome of the first flip if we flip the coin 2 times? Okay, so we think about, all right, what are the possible outcomes I could get? I could get heads followed by heads. I can get heads followed by tails. I could get tails followed by heads, and I can get tails followed by tails. So there are 4 possible outcomes. And we can say, all right, which of these satisfy the condition that the second flip matches the first flip, okay? And that's going to be heads, heads, or tails, tails. That satisfies the condition where the second flip matches the first flip. And in this outcome, heads, heads is mutually exclusive of tails, tails. I can't get one outcome and at the same time have had the other outcome. So we're going to say, all right, this is going to be the probability of heads, heads, or tails, tails. And this is going to be the probability of heads followed by heads, which is 0.7 times 0.7. This is probability of tails, tails is probability 0.3 times 0.3. And I get 0.49 plus 0.09. I add those two together and I get 0.58. 0.58 there. All right. Okay. We're feeling okay about this stuff? All right, and I'll just do, I think, one more of these examples here, sequences of independent events. All right, this time I'm going to flip the coin 4 times. All the coin flips are independent of each other. What's the probability I get heads all 4 times, right? What's the probability I get heads all 4 times? Every time I flip the coin, it's going to be 0.7. So we need the probability of heads, 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 heads. It's going to be 0.7 times 0.7. I can just do 0.7 raised to the 4th power. And it's going to give me something around 24%, 0.24%, 0.2401. Okay, and we're just multiplying all of these independent probabilities together. Okay, we got to talk about random variables. We got about 15 minutes to get this in. I think we can do it. Okay, so we've been talking about probabilities, random events, and things like that. And a random variable is basically a special kind of outcome to a random event. It's the outcome to a random trial, but that outcome has to be a number, okay? It has to be a number. And then we can talk about it being a random variable. So a couple example, we can say, I'm going to pick a person at random from the room. That's the random trial. But the outcome has to be a number. So it can be, what we're going to do is we're going to write down the person's age. Okay, person's age in years or something. That's a number, right? And we said we're going to pick a person at random from the room and we're going to write down the person's hair color. That would not be a random variable because hair color is going to be a categorical variable like brown hair or blonde hair or black hair or something like that. That's not going to work as a random variable. It has to be a number. So we can write down the person's age, the person's height, the person's, how much money do they have in their wallet at that exact moment. Okay, it's a number, and a random variable has to be, you're doing something random and you're writing down a number. Another example is we can say, I'm going to flip a coin 6 times. That's the random part. And the number we're going to write down is how many times it lands heads, right? So that's a number, right? We could say it landed heads 3 times out of 6 flips. It landed heads 5 times out of 6 flips, okay? And oftentimes when you're dealing with random variables, you want to know something like what's the mean of the random variable or the expected number, expected value of the random variable. And you can think of that as, if you were to repeat the random trial many times, and then you write down all of the outcomes, and then you say, let's take the average of all of these outcomes, like an infinite number of these things, that would be the expected value or the mean. Okay, we can also talk about the standard deviation and stuff. So to calculate the mean of a random variable, we call the symbol we use for that is mu. This is the Greek letter mu. It's the Greek letter for the, I guess, the letter M. We can also say the expected value of random variable y. Capital Y means random variable y. The expected value of random variable y is mu. And the way we calculate this, you don't need to be worried about the formula, is you're going to take the outcome, one particular outcome, and there's, I guess, n different possible outcomes. You're going to take the outcome of getting a certain value, and you're going to multiply it by the probability of getting that value, right? So you find the mean by taking each particular outcome, yi, and multiplying it by the probability of getting that particular outcome, and then you're going to add them all up. Okay, so let's do an example here. All right, so the idea here is okay. This is some game, okay? And this is a terrible picture here, okay? And you're gonna kind of just spin an arrow, okay? And if it lands over here, you get 0. If it lands over here, you get 1. And if it lands over here, you get 5. Okay, so you spin the arrow, depending on where it lands, you maybe get 0. So the probability of getting 0, that y equals 0, is going to be 0.5. The probability that y equals 1 is going to be 0.4, and the probability that y equals 5 is going to be 0.1. So what is the expected value? The expected value, mu, okay, is the sum of each outcome multiplied by the probability that y takes on that particular outcome. So we say, okay, the first possible outcome is 0, and what's the probability I get 0? Okay, we're going to multiply that by the probability of getting 0, which is 0.5. And then we say, okay, what's the next outcome I could get? Well, the next outcome I could get is 1. And what's the probability I get 1? 0.4. Okay, and what's the last outcome? The last outcome I can get is 5. And what's the probability I get 5? That happens with probability of 0.1. Okay, all right, and so you multiply these out, 0 times whatever is 0. Here I get 0.4, and 5 times 0.1 is 0.5. And therefore, our expected value, or our mean, mu, is 0.9. And so what this means is that if you play this little carnival game where you kind of spin the wheel, or you spin the arrow, or whatever it is, and if you were to do this like a bajillion times, the average of your winnings is going to be around 90 cents, okay, 0.9, okay? Sometimes you'll win $5, sometimes you win $1, sometimes you win 0, and overall, the probability that you're going to win, not the overall probability, the overall amount, the average amount you get is going to be 90 cents, okay? Of course, any one game you play, you're not going to get 90 cents. You're either going to get 0, 1, or 5, but the average after many plays is going to be 90 cents. That is the mean. Okay, and so here's the math here on that slide to get that. Okay, so I've been told that when I handwrite these things for the math, like that's helpful as far as keeping you engaged and following along, rather than just kind of like flipping through the slides and saying, "Ta-da, here's the answer." So I'm still doing that. I'm going to keep doing it. Okay. All right. We can also ask about the variance. Okay, so the variance and the standard deviation would be the square root of the variance. The way we're going to find this, the symbol for the variance is sigma squared, and we're going to take. You first have to find the mean or the expected value, and we're going to take each value, subtract off the mean, square it, multiply it by the probability of getting that thing, and we're going to sum them all up. Okay, so let's go ahead and try this out. Okay. So, so here the formula again is yi, each value, minus the mean, and so we've already found the mean. So we know that the mean is 90 cents. Okay, and so we're going to go through each outcome. So the first possible outcome is 0. We're going to subtract off the mean, 0.9, we're going to square that, and we're going to multiply it by the probability of getting 0. Okay. Okay, we do that to the next possible value. The next possible value is 1. We subtract off the mean, 0.9. We're going to square that difference. We're going to multiply the probability of getting 1, and that's 0.4. And then the last outcome is we can get 5. We subtract off the mean. We're going to square it, and we're going to multiply by the probability of getting that outcome. Okay, so 0.9 squared is 0.81 times 0.5 plus 1 minus 0.9. This is 0.1. 0.1 squared is going to be 0.01 times 0.4. And 5 minus 0.9 is 4.1. What is 4.1? 4.1 squared. 16.81 times 0.1, okay? So 0.81 times 0.5 is going to be 0.405 plus 0.01 times 0.4 is going to be 0.004 plus 16.81 times 0.1 is going to give me 1.681. I don't know what this is. Let's come over here. 0.405 plus 0.004 plus 1.68, 2.09. That's my variance. Is that okay? How I arrived at this number. Okay, so that's great. Here's a formula, right? And here's the numbers that you plug in. But what does this mean, right? So let's take a look and see, like, what does it mean to have a variance and things like that. Okay, so here I've got I'm comparing 2 random games of chance. Okay, and the wheels basically. So one, all right, so one wheel, okay, I want a wheel here, and we're gonna have a wheel here. And so one, you got 50% chance, and I don't know how to draw. Okay, we're gonna say it looks like this, right? And so this one, 50% chance you get, you get 0, 0 over here, 1 over here, and 5 over here, okay? And the mean here, if you do it, is going to be 0.9. Okay. And over here, we've got something that looks like this. Okay, okay. So you're going to get 0 over here. You get 1 over here. And in this tiny piece, you get 800. Okay. And it's probably even smaller than this, right? It's this is probability of this is 1 in 1,000. Okay. Okay, so both of these, if you do the calculations, the mean of this one is also going to be 0.9. Okay, so both of these have an expected winnings of 0.9. Okay, if you do the calculations here for this one, you get 0 times 0.899, 1 times 0.1, 800 times 0.001. And so you get 0 plus 0.1 plus 0.8. You also get 0.9. Okay, so both of these games, if you play both games infinitely many times, on the average winnings is going to be 90 cents for both of these games. Okay, the average is going to be 90 cents for both of these games. Okay, which game is more exciting to play? The one where you have a chance at winning $800, right? Like this one, it's like half the time, like let's say it costs $1 to play the game, right? Half the time you get nothing. 40% of the time you get your dollar back. That's not exciting. And then like 10% of the time you get $5 and you go, all right, I got $5. I guess I should be happy. Okay. Over here, you play the game and kind of like, okay, most of the time, this is like buying a scratcher at the gas station, right? It's like you buy the scratcher knowing full well most of the time you're going to just lose your dollar, right? You know full well that you're going to lose your dollar. Sometimes you get like a free scratcher, right? You go, oh, okay, oh, I can play the game again. You know, that's like getting your dollar back. But then just every now and then, there's a very slim chance that you might win something like $800 or $1,000 or something like that, right? This game is a lot more exciting, okay? And it's going to get reflected when you do the calculation for the variance, okay? Here you do 0 minus 0.9 times that probability, 1 minus 0.9 times the probability. And this one, look at this, 800 minus 0.9. When you square that, you get this huge number. And even though you multiply it by this tiny probability of 0.001, the overall variance ends up being much bigger, 639.29 versus the variance of this game is only 2.09. Okay, so the variance over here is 2.09. The variance over here is much bigger, 639. Okay, and basically, psychologists and people who study gambling and stuff like this say this kind of game is much more exciting. That that people, you know, the reason why lotteries are so successful is because it offers just a tiny chance that you might win like $100 million. Okay, and if you do the calculations, the mean payout for like a lotto ticket is probably like 50 cents or 40 cents. It's really bad. You know, most of the dollar money that goes into the lotto gets taken by the lottery agency and doesn't actually like make it out to the people who play, right? But they offer just a very tiny chance that you might win a huge amount of money, and that keeps it very popular. Okay, whereas, you know, a game that has very little variance is much less popular to play. Okay, so, you know, and you can kind of see this if you ever go to like an amusement park and they kind of have like that boardwalk area. You know, how do they get people to play? They have giant prizes advertised, right? Like you got the giant stuffed animal. Okay, and then there's other games where it's like everyone's a winner, or like a winner every time we play, and those prizes are little. And then I think those games are a lot less popular, right? Because it's just kind of like, I might as well just buy that souvenir for $5 anyway. Like that's not as exciting versus like you have a chance at winning the giant teddy bear or stuffed animal or something like that. Okay. And so that's kind of how it goes, right? So both of these games, if you do the calculations, they have the same mean, but one has a grand prize that's much more valuable, hits at a much lower probability. The value is much more extreme, so your variance is much greater in that situation. Okay, all right, that's the end for today. So we will end our lecture here, and we will see you guys on Monday. Okay, so please remember to take your quiz this weekend. Make sure you submit your homework, and we will see you guys on Monday. So have a good evening. I'll also stick around for office hours as needed.